Thank you, Christian. I don't see it on the screen yet. Oh, here it comes. All right, it's great to be here. My name is Simone Gasparinetti. I'm associate professor at Chalmers University of Technology in Sweden. Thank you, Christian, and everyone. This is a great event, a great crowd. I'm honored to be here. Thank you. The group I lead, it's called the 22Q Lab, based in Chalmers. We are an experimental group. We work with circuit QED. We have 3 main research lines. We do quantum computing with bosonic modes, which you've heard some in the yesterday's session, not from our group. And then we do quantum thermodynamics, which is the main topic of my presentation today. We're also working with several types of quantum enabling technologies, such as amplifiers, cryogenic switches, and infrared blocking filters. We also spun out a small company, it's called Sweden Quantum, which commercializes these filters. I also want to advertise, we had a poster presentation on Tuesday by Lukas Splithoff, our postdoc, also a former Delft graduate. We have developed a quantum design optimizer tool, which we find very useful. You can find the manuscript on the archive. Go download our open source package on GitHub, and Lukas should still be around, and that's what he looks like if you want to ask more questions. I also should acknowledge the people in my team and collaborators who contributed to our quantum thermodynamics activities, especially Amir Ali, who is a senior researcher at Chalmers, and Simon Sunderlin, who is a PhD student. We also have an ongoing collaboration with Nicole Junger-Halbern at NIST and University of Maryland, and some of our conversations were instrumental to getting this work started. So in the context of this conference, I would like to briefly review what we mean by quantum thermodynamics. And I will start it by referring to classical thermodynamics, which is a foundational theory in physics. It was developed long ago, the heyday of the Industry Revolution, to explain how systems with many degrees of freedom could actually be described by very few quantities. And this theory explains successfully, for example, how heat engines and refrigerators work. Then, and this is already history from a few tens of years ago, as we managed to miniaturize machines of various kinds, we started looking at systems in which the degrees of freedom are not so many and fluctuations become bigger. So systems that are a bit further away from the thermodynamic limit. And this is where this field, which is now known as stochastic thermodynamics, was born. And especially in the 90s, we saw lots of experiments on these small systems, looking at how fluctuations behave, looking at things, for example, as a Jarzynski equality. And these systems are individual molecules, colloidal particles, and also single electron devices, metallic islands or quantum dots. What we're trying to do with quantum thermodynamics here is to look at how genuinely quantum effects, so the same effects that underpin the quantum computer, would play a role in thermodynamics. And the platforms that we can use to study these systems are the very same that you're thinking of when you think of a quantum computer. So we can think of cold atom, trapped ions, and of course, superconducting circuits. There is a general attempt after decades of theory work to try and make this field more useful. And I think this could be done in 2 different ways, which I will describe now. We could try to seek for quantum advantages in thermodynamics. For example, many people in this room are convinced to build a quantum computer because you know you can run Shor's algorithm at some point. So you can have a fundamentally proven advantage in scaling. And does something like this exist in thermodynamics? Can you build a quantum-powered machine which beats any classical machine at something? Be it the power output of the machine, the charging speed of a battery, the precision of a clock. So this is very interesting because it would provide a fundamental foundation to the field. And it's still an open question. At the same time, we could also focus on more practical applications and just try to build a quantum thermal machine which you deploy in a useful setting to do something useful. And what we try to do in my lab is actually a little bit of both. And I will show you some examples. So this is a brief outline of the remainder of this talk. I would like to explain how we use the superconducting circuits you're so familiar with to do quantum thermodynamics experiments. And then I will show, time permitting, 3 examples One of these you might have encountered because it's in the very context of circuit QD and computation. It's the thermal reset of a superconducting qubit, which we published in Nature Physics this year. And then something which is a bit more fundamental, a quantum heat engine which is powered by diffusing noise. And also what gets us quite excited lately, measurements of tiny heat current fluctuations that might violate classical bounds in thermodynamics. So let me start by quickly reviewing how we apply circuit QD to quantum thermodynamics. You are very familiar with circuit QD here. I mean, in this context, the angle I take is that of quantum optics. So we use the nonlinearity of the Josephson circuit to build synthetic atoms, which act as emitters, and we use microwave resonators and waveguides as light modes. And what's interesting about this platform in this context is that these interactions can be made very strong and also tunable, both at the design stage and in real time. We combine this circuit QD platform with quantum thermodynamics. And here the quantities of interest are things such as heat, work, and fluctuations. And this sketch essentially is a sketch of a classical machine in which you have particle reservoirs as heat baths. You have, again, a system of particles as a working medium, and you have a work repository as a piston. What we do in quantum thermodynamics is replacing this classical working medium with a quantum one, for example, a small ensemble of qubits, while keeping the baths and the work repository classical. So this is how it would look like. And here I'm starting to introduce a little bit the specific scheme that we use to achieve this. So this is a small qubit ensemble. It's coupled to waveguides. It can be driven coherently. And these waveguides, which we typically try to make as cold as possible, in this particular business, they are actually intentionally overheated to emulate baths at the given temperature. We do this by injecting classical noise and having this noise mixed with quantum fluctuations as noise goes down our chain of attenuator. In particular, the last attenuator has a cold resistor whose noise can be described only quantum mechanically. These thermal baths interact with the qubit ensemble, they are scattered, and they are routed via circulator to power spectrum analyzers. So this is our architecture. It's a bit flipped compared to what you're usually thinking, because we're actually interested in how the qubit ensemble scatters thermal fields. And we're going to be looking not much at the qubit themselves, as at the scattered fields. This is one step closer to implementation. We see a transmission line, we see a single transmon qubit, a circulator, a cold attenuator, and a noise source. This thing all together is what we refer as an emulation of the heat bath. And we can notice that this heat bath has some interesting properties. For example, as you know, a waveguide hosts a continuum of modes with an ohmic spectral density, which is a textbook thermal bath you find when you look at derivations of master equations, for example. We can synthesize the spectral occupation arbitrarily because we can decide to inject noise at different frequency. So we can have different transitions heated at different temperatures. Plus, we have the opportunity to analyze the scattered radiation, both as an integral, but also in a frequency selective way. Our first experiments in this direction, they had to do with the validation of this concept. For example, we wanted to know that if we apply synthetic thermal radiation, the qubit perceives it as a thermal field. And this is work we did already back in 2020, summarized by these two plots. Here we are showing that as we heat up this waveguide, the qubit reflection coefficient changes according to our theory, which is in solid line on top of the experiment with no fit. While the plot on the right shows that if we heat up physically the attenuator by heating up the mixing chamber, our thermometer correctly predicts the temperature over a range of parameters. So this establishes an equivalence between heating up the attenuator physically and controlling the effective temperature with synthesized radiation. Let me now show the first example of a machine which we built. Which is a thermal machine that is used to reset the superconducting qubit. I don't need to motivate qubit reset here. It's obviously a necessary primitive for computing and something many of you are working on. There's two ways to do it that I know of. You can do it actively by measuring the qubit with a high fidelity and conditionally flipping it, Or you can do it unconditionally, meaning that you would couple the qubit to a thermalized cold mode, which would take away the entropy of the qubit, resetting it to the ground state. Both these concepts were, of course, already explored in circuit QED. Active reset, I think one of the first realizations from Leo Di Carlo group here, back to 2012. And also, there are many experiments on unconditional reset. One such was performed by some of us when I was back at ETH. And the idea here is to use combined coherent drives and dissipation to funnel the qubit excitation into a cold mode, this resonator in this case, which would then decay to the ground state. So this is quite close to an autonomous machine, but not quite yet, because you're still using coherent states. And coherent states, they are an expensive resource in thermodynamics because they have a definite phase. So if you're a purist of thermodynamics, you wouldn't call this an autonomous machine. The only free resource in thermodynamics are thermal gradients. So this is a purist perspective. If you want to take a more applied take, you could also think it's very expensive to drive these coherent tones from room temperature all the way down. And what if we could use the natural gradients in your cryostat to reset at once an ensemble of qubits? That would be quite convenient. So this could be an applied, more applied take to this approach. What I will show you now is the thermal machine that we build to reset the qubit. And this machine is based on a known concept in thermodynamics. It's called the quantum absorption refrigerator. If you focus on the oval here, I'll take a moment to explain how it works. Imagine you have a 3-level system in which each of these transitions is coupled to a different bath. And now the transition from 1 to 2 is coupled to a cold bath, and the one from 1 to 3 is coupled to a hot bath. It could still be that this population is lower than this, because even if the bath is hotter, the gap is larger. And then once you introduce a high temperature field that would equilibrate these transitions, the net effect would be to take heat out of the cold bath and into the hot. And if you follow through this explanation, this is how the quantum absorption refrigerator works. We implemented a circuit QED version of this. It looks like this. This is a target qubit we want to refrigerate. And then we have 2 additional auxiliary qubits coupled to a cold and a hot bath. And the ingredient we miss here is a 3-body interaction, which would take excitations from the target and the hot and dump them into the cold. So this thing all together, it would be the quantum thermal machine, which is stitched to the qubit to reset it. This little sketch will show you what happens. So if qubit target is excited, but this hot qubit is empty, nothing happens. But as soon as we excite them both, the 3-body interaction will funnel the excitation into the cold qubit, which will eventually decay into the cold reservoir. And because this is cold and strong coupled, the reverse process is inhibited. And this is how we take entropy away from the qubit and put it in the ground state. This slide shows our experimental implementation, which is a custom-made 3-qubit superconducting device designed and manufactured by us. Our first experiment I show you is to demonstrate that we have this static 3-body interaction. And by the way, a technical detail to implement it, we use static 4-wave mixing. So we take 2 excitations away from the 2 qubits and dump 2 excitations in the middle one, which actually acts as a Q-trit. As you know, 4-wave mixing is the most straightforward interaction you get out of Josephson junctions. This plot is meant to demonstrate that we do have a 3-body interaction at place. We are sweeping the frequency of a driving tone we put to qubit 1 and the frequency of qubit 2. We have excited qubit 3 and we look at its population. So this shows that essentially when we drive qubit 1 at a certain frequency and qubit 2 is at the resonance, we can effectively deplete population in qubit 3. So this is our cleanest evidence of a 3-body interaction. If we now sit at this resonance and plot the population of the qubit versus time, we see that essentially by increasing the strength of the drive on qubit 1, we can control the lifetime of qubit 3. So this would be already an unconditional reset operated by a coherent drive. The final step we need to take is to swap the coherent drive with a thermal field. And this we do in this slide, in which instead of driving the qubit coherently, we subject these qubits to thermal fields of different temperatures, which we sweep in this plot. This plot shows the population of the target qubit as a function of time. We have a log scale here and linear scales with different pitches to decouple the long-time dynamics and the short-time one. So this plot is a little difficult to read, sorry for that. What we can see, nevertheless, is that the lifetime of the target qubit drops dramatically as we make the hot bath hotter by changing its thermal occupation. I will give you some numbers here. By this mechanism, we can reach a steady state population of the target qubit down to 3×10⁻⁴, bringing it an effective temperature of 22 millikelvin. And we think this is a very competitive number in this day in circuit QD and quantum computing generally. At the same time, we notice the reset time is a bit slow because of the way this machine works. So we reach a 1% qubit occupation in 970 nanoseconds. And of course, we would like it at least 3 times faster to be competitive with current approaches. Notice, however, that this is a proof of principle. And for comparison, if we were just letting the qubit sit on itself, we would get 2.8% thermal population, corresponding to 50 millikelvin. And if we were trying to directly connect the qubit to the waveguide, which sits at 45 millikelvin, we also would get 2% population. While with our thermal machine, we get 3×10⁻⁴. So this is really operating as a quantum thermal machine, creating an object which is colder than anything else you have around. Let me move to the 2 remaining examples. And let me just check how much time I have. All right. So this is, let's say, a little less in the applied and a bit more in the fundamental direction. We wanted to see if we can implement this concept of a Brownian refrigerator, in which essentially you have a machine that, when subjected to noise, takes heat from a cold bath and brings it to the hot. So these refrigerators were proposed many years ago, but not experimentally realized yet. So we built what we believe is the first realization of this concept, leveraging the quasi-thermal fields in waveguide that I discussed. There was also previous work in the Wallraff group about noise-assisted energy transport. This is something that is studied, for example, in quantum biology. And then we used a little trick, which some of you in Circuit QD will appreciate, which is called the symmetry-selective couplings. So now I will take a minute or two to explain what these symmetry-selective couplings are about. Maybe you'll find use for them in some of your applications. The idea here is that we have a quantum system coupled to 2 waveguides, and we would like to create our own selection rules. In particular, we're interested in a V-shaped system in which this transition is coupled by symmetry only to this waveguide, while this transition is coupled only to this waveguide. We can achieve this by having 2 qubits that are strongly coupled. So these are, for example, 2 split transmon with a strong capacitance in between. Of course, when resonant, they will hybridize, and they will form modes that oscillate in phase and out of phase. And now we can couple the waveguides selectively to some points so that we use constructive or destructive interference to enhance or suppress the coupling. This concept is quite similar to giant atom intrinsic Purcell filters, and many ways people in the field are exploiting interference between multiple points to achieve suppression or enhancement. In summary, what we can create here is this V-shaped system with selective rules in which each of these states is bright to one waveguide and dark to the other. Here is how we're using these symmetry selective couplings, which, by the way, we're using for many different experiments, to implement a dephasing assisted refrigerator. So the system looks like this. It's 2 strongly coupled transmons. And here you have flux lines to control the frequencies, and the 2 waveguides selectively coupled. We notice that dephasing does not transfer energy in the qubit basis. But once these systems are strongly hybridized, it has the potential of equilibrating the populations between these 2 levels if the noise is provided as a frequency difference. So by injecting noise, which is not zero frequency noise, but finite frequency noise, we can thermally induce the equilibration between these two levels, which in turn, because each of them is coupled to a waveguide, will introduce heat transport. The way we can demonstrate this is by looking at noise-mediated power transfer between the two waveguides. So we start as a situation in which is the power spectral density from one waveguide, and nothing happens in the other place. But then, as we increase the noise, we see the reflected power goes down, and the transmitted power goes up. So this is power transferred mediated by finite frequency noise. And then if we play this game for various temperatures of the two baths and various strengths of the noise, we can implement a thermal machine that has different regimes. So this is a heat flow across the baths as a function of the ratio between the temperatures. And depending on this ratio, we can have a heat engine, we can have a refrigeration, and we can have a heat acceleration mechanism. Notice the extreme low scale at which we appreciate power spectral density and the scale of the heat flows, which is a fraction of an attowatt. And this we still do with linear amplifiers, but with dedicated signal processing. Let me give you in 1 minute just a little summary of our latest experiments. We are trying to measure not just the power which is transferred by these systems, but also the fluctuations. And this we do by analyzing the statistics of the integrated current and the variance. There is something which is called thermodynamic uncertainty relation. It tells you how much entropy you have to dissipate for a system to be precise. And this is bounding the diffusion coefficient of these statistics to the entropy production. So if I want this distribution to be sharp, I have to dissipate lots of entropy. We think we can beat this with a quantum system. This would be one of the very first fundamental proofs of quantum advantage. We do it in a device which is similar to the previous. And I'm just going to skip some details and jump to the conclusions. This is a plot of the quantity we want to violate as a function of a parameter. So this red line is the classical bound. The green dots, they're our experiments, and the dash is a theory with no fit parameters. So we're really approaching the classical bound here, and we hope to beat it in the next generation of devices. I'm coming to my summary. What we do here, we're building quantum thermal machines using circuit QD. And then you have a unique methodology to measure these heat flows. I gave you 3 examples, and I also tell you what we're working on. What we have in the pipeline is a violation of the TUR, autonomous quantum clocks, replacing these quasi-thermal fields with thermal fields, and also implementing photodetection instead of linear amplifiers, because that's more suited for these measurements. Thank you very much for listening.
Thank you, Simone. We have time for some questions. Yes, here.
Thank you for the great talk. I have a question on one of the first slides. You showed the schematic, and there was the quantum noise being split with the thermal noise. Could you tell what's the quantum noise there?
Yes, I mean, essentially classical noise is at infinite temperature, like the 2 processes of absorption simulated emission are the same. You don't see kind of spontaneous emission, right? So this is deep in the quantum limit. This, if you think of a resistor, for example, you have the Johnson-Nyquist noise, which is classical noise, but this does not accurately describe the system when the average thermal photon is less than 1. So what is happening is that your noise is getting progressively more quantum as you go down the attenuation chain.
Oh, thank you.
So if you admix, let's say, a purely quantum noise, suppose your resistor is in the ground state, and with infinite temperature noise, you get something that closely resembles quantum noise, in brief.
Thank you.
Great. You can pass it forward there.
Thank you for a very clear talk. Thank you so much. On an earlier slide, you mentioned the reset success fidelity, and it was very low. And I have a feeling that so small probabilities will be maybe start of the new field, like metrology of fidelity, because it's so hard to measure so small probabilities. Can you maybe comment a little bit on what it takes to measure 3 × 10⁻⁴ success probability?
This is a very interesting question because I think in this community some people have started to appreciate how difficult it is to actually measure such a small residual qubit occupation. There is a method, some of you know, it's based on playing Rabi pulses assisted by the third level, which has been used by a few groups. And of course, if you think you're great at single shot, you could just sort of analyze the single shot statistics. But to appreciate such a small population, it would require at least 3 nines of single shot fidelity, which not everyone has.
And it is really hard also due to systematic errors because your readout has side effects which you need to like compensate for. Like you have to do some readout error mitigation, which introduces also systematic errors. So it really becomes like a field of metrology to measure so small problems.
I completely agree. And in the supplement of the paper, we give some details exactly how we can bound. Actually, we say 2 10 to minus 4 plus minus 2 10 to minus 4.
Thank you.
It's a big error.
Awesome.
It's more like a bound.
And
it's
it
very
will be
difficult.
even more interesting as probability goes lower.
All right.
Yeah, thank you.
Thank you.
Great. We have a question all the way over there. Great row.
Thank you very much for the talk. I was just curious whether you could comment on what limits the duration of this qubit reset. Is it just the temperature difference between the hot and the cold qubit, or what is it that limits it, and how much do you think you can improve it?
Right. It's a good question. I mean, this is a cascaded process in which the first qubit is randomly excited by the thermal field, and then the three-body interaction with strength is a couple megahertz. In this case, is funneling into the cold, and then it has to decay. The bottleneck in this problem is the thermal excitation of the first qubit, because actually you want this bath to be weakly coupled and very hot. And I think we can beat this trade-off with some refinements. We were overly cautious in the first implementation. Generally, thermal fields are a bit slower than coherent drive, but not much so.
Okay, thank you.
Thanks.
Great. Then let's thank Simone again. Good.